So let's take a look at the mechanism for the Heck reaction. It's going to have a lot of steps that are familiar to us, like the oxidative addition and reductive elimination and all that. Although there will be two more steps where we will have our alkene do a syn addition onto the palladium, and we're also going to have that alkene undergo a syn elimination. And we're going to see that those two syn steps are going to potentially lead to some interesting products. For this mechanism, we're going to use an alkene that's typically not very good for the Heck, but it'll show us very clearly that those syn steps involved here. So, our first step, as always, we'll go ahead and start, and I will be good and use my purple for the palladium. We're going to have our oxidative addition. That's the first step of our vinyl triflate. So we're going to go ahead and add that on. And again, we can kind of just say R here. That works. We'll have our vinyl group be an R. So we'll have our palladium. We'll have it with its two ligands. And we will have the triflate and the R group here. Great. So next step, we're going to have the syn addition of our alkene onto that palladium. We're going to see that the R group and the palladium are going to both bond to the alkene. There we go. So this is going to be a little bit interesting. So we'll draw our palladium. We'll draw that first just so we can have it out of the way. And we've got it with our triflate on it. When we bring in our alkene, what we're going to draw is we're going to have our new bond to the palladium. I realize our alkene should be in blue. So we're going to form a bond to the palladium onto our more substituted carbon. So we're going to have two methyl groups on here, which we will put with stereochemistry. So we've got those two methyl groups. On the other side, we're going to have our original methyl group. And now we're going to have our R on there. So we're going to end up now replacing that hydrogen with an R group. So we'll still have our same methyl group on there, and we're going to now add the R group. So here's our hydrogen back there. So we have everything now. Our alkene is in there. We've added our R group and our palladium onto it through a normal just alkene addition. So this is a syn addition. We've added our R and the palladium to the same side of the molecule. So that's why those two are on the same, in this case they're in the plane, but they could be either on wedges or dashes. But they would have to be the same. So put them both on wedges, both on dashes, both on normal, regular, in the plane lines. Either way works. So this is the syn addition here. Great. Okay, now what we've got is this has to be a syn elimination. And in order to get a syn elimination, we need our palladium and the hydrogen to be on the same side. All right, syn, meaning same side. So our palladium currently is on a regular line. Our hydrogen is on a dash, so we're going to need to do some rotation. So as we rotate this, we're rotating this R group carbon, we're rotating that around. We need the hydrogen to be in the same kind of phase as the palladium. So we could rotate that back carbon 120 degrees kind of towards us. So the R group will move to the wedge, that wedge will move to the dash, and the hydrogen will come out to the in the plane. So our palladium here, we'll copy that. This is the tricky part for this reaction. So we have our wedge and dash on that carbon. Once we rotate this again, we're going to have that hydrogen be in the same plane as the palladium. Our R group, therefore, will be moved to the wedge, and our methyl group will be now on the dash. So we've just rotated that carbon. We have rotated that back carbon. Great. Now our base comes in and will remove this this hydrogen. We'll end up with our elimination happening. So we'll have that syn elimination. And in doing so, we're going to kick out our product, which is going to be the R group now on there. Everything else stays the same, so we still have our methyl groups on that alkene, so we've kicked them out now. And we're going to have our palladium, purple for this. These mechanisms can be so tricky. But our palladium, it now has the hydrogen and the triflate. And now what we need to do is just have our base come in and kick it out. So our base will grab the hydrogen and kick out the triflate in a reductive elimination. That's the last step here. So our base just comes in and will kick out what did we use as our base? Acetate. So we'll have the acetic acid come out along with our triflate. So we'll kick both of those out. So essentially our base comes in. I don't want to clutter this too much, but we'll look at that last step. So our base comes in. It will kind of grab and we're going to regenerate our palladium. So we're reducing it back down again. So it's reductive elimination. So we're giving it electrons, right? So that's that last step. We're just kicking our hydrogen and our X out of the palladium, and we're regenerating our catalyst, allowing it to continue again. And so this leads to some interesting stereochemistry outcomes with rings, or rather regiochemistry outcomes. And again, this is something I want you to try on your own. See if you can't figure out why this is happening here. Why does, if we try this alkene plus, say, I don't know, make this nice and simple, and we'll try our triethylamine. Why does this one add in this manner? Why do we end up, instead of installing it on our alkene that we normally do, why does this one install slightly different? Again, let's look at what normal product would be. The normal product is we'd install it directly on that alkene. So we would expect that we would just get it normally there. So why do we end up with that top product? And I would suggest this one, take a look at the, remember that rings cannot rotate. So that's our clue here. So because rings cannot rotate, we'll see why we end up with this product. So again, try that on your own and then look at the notes later for why that has happened. So, and then in our next video, we'll cover our last section, which is on the Grubbs metathesis.